Okay. Um, I don't know. We're only up to 26, but it's 2 minutes after. So, um, last time, um, we talked about how the rule. Well, we talked briefly about how the rules define the arrow relation for the big step semantics. And so for A expressions, which is a really simple, dumb language, but it gets more complex as we add more things. So here's the simple language is that we've got numerals, which remember are some kind of representation of an integer. Terms that are A1 plus A2, where A1 and A2 are the left and right subtrees of that abstract syntax tree. A minus with a left subtree and a right subtree, a times with a left and right subtree, and the ability to put any A expression inside parentheses. So I mean, if I could write, I would say like, the label on this one is not times or minus or plus, but it's left paren, right paren, and it has a single subtree, and that single subtree is whatever is written down inside the A expression inside the parentheses. So when we say that the rules define the arrow relation. So I mean, he gives you, I don't know if I have it on the next page. No. He defined, then he says, okay, what's the transition relation here? Well, the configurations are either A expressions or they're integers, so that's our big gamma. And then the arrow relates A expressions to ints. Both of them are in gamma, so that's okay. But we don't have any rules in here, or we don't even have any syntax for just pure integers. And then it says arrow is the relation defined by the rules, and that the terminal states or the terminal configurations are the integers, which is also a subset of gamma. So that all follows the definition of what a transition system is. So you have to think about, like, it's not entirely clear what he means by these rules defining the relation. So first of all, I've kind of collapsed a lot of the rules by combining the rules for plus, times, and minus into one rule where I'm using a little symbol for whether it's a plus, a times, or a minus. So I can write down this one rule. And then over here, you'll notice that I say, okay, and then V is equal to V1, and then use the meaning function left right bracket defined as follows to get the operator to use, and apply that to V2. So in the case that the operator is plus, the meaning of plus is mathematical plus. In the case that the operator is minus, the name of the rule is minus BSS. This would be a minus, and then the meaning of minus is mathematical minus. It maps you to that mathematical function. And then times BSS, this would be a star, and over here, the meaning of star, he has as the dot, a single multiplication indicated by a dot in between the arguments. So this is a nice way to kind of syntactically collapse three rules into one. And then we still have the parent rule that says, oh, if I have an A expression inside of parentheses, that evaluates, and that is in the relationship to the integer v if a is in the relationship to the integer v. And for numeral n is in the numeral is in the relationship to the integer v if v is equal to this funny thing, which basically says map the numeral to its actual integer meaning. I should maybe read over this one up here because these are all the same, even though they're because they're all the same, we can collapse them. There's plus, minus, and times. So let's just take plus. If I want to say that A1 plus A2, following the big step semantics arrow is in the relation big step semantics arrow to an integer v, I have to show that the sub-expression A1, which is also an A expression, is in the relation, the arrow relation with V1, and that the sub-expression A2 is in the integer, or the arrow relation with the integer V2. And if I take those two integers and perform real mathematical plus on them, I get back V, then that means that A1 plus A2 is in that relationship with V. So, okay, so it looks like something's going on here. There's some kind of tree structure that we're building. And these are the proof rules. And what we're going to do is we're going to use the proof rules to use derivations that show that, in fact, some concrete formula. And what I mean by concrete is that if you look at the syntax up here, we've got n's and A's, ones and A2s, and I don't know, I guess that's an A1 there. So we've got these symbols in there, but no actual A expression has an N in it, or an A1 or an A2. They're all something that look like this. There are no N's, there's no A1s, there are no A2s. You have to completely instantiate. Now, if we had variables, you might be able to write something that looked a little bit more like these things up here. But for now, we don't even have variables. The only thing we can write are arithmetic expressions where the operands to the are either, well, subtrees of A expressions, or they're at the leaves of these trees are always going to be numerals. And you can sort of see that up here because this is the only rule that doesn't kind of depend on the arrow, using the arrow relation to it. This is the base case. And so that means the leaves of all these abstract syntax trees are going to have numerals at the leaves. This one here is inductively defined. We're defining what it means for the A expression A with parentheses around it to evaluate by V by using B in the relation arrow, which is the big step semantic relation, by saying, oh yeah, it's in there if A, when I strip off the outer parentheses, is in the big step relation. So this is defined recursively, essentially. This evaluates to this if this evaluates to this. And this is a smaller expression because I've ripped off the outer parentheses. And then up here also, there's an induction, there's a recursion built in this inductive definition that basically says, look, it has to be the case that A1 and A2 are smaller A expressions. And what do I mean by smaller? Well, I mean, you could just like count the number of numerals that occur in the A expression. You have to have at least one here because the leaf of every tree is a numeral. You have to have at least one here because the leaf of every tree is a numeral. So this thing here has at least two numerals in it. And this one has at least one, and this one has at least one. But no matter what, if we calculate the size by counting the number of leaves in the tree, This is going to be smaller. The size of this one's going to be smaller. The size of this one's going to be smaller. And that's the justification that eventually, since everything keeps getting smaller, whether we use this recursion defined by this inductive rule or the recursion defined by this inductive rule, eventually we're going to get down to a case where it's a numeral evaluates to a variable. So to show, so that's sort of the justification that there's no A's in an actual expression of type A expression. That is just meta variables used in the grammar to help you describe all the terms that are in there. So now if we want to build a derivation tree, and we'd like to show that, for example, now, I mean, you can do it in your head, but once things get more complicated, the derivation trees are going to be useful. So you can look at it, you can see like, okay, we remember that our rules are our rules are of the form A expression, arrow, integer. And so if I want to show you that in fact the numeral 5 added to the numeral 1 parentheses times the numeral 8 minus the numeral 9 in parentheses evaluates to -6, I have to build a derivation tree using these rules. These rules are defining what the meaning is of this arrow relation. And remember, big step evaluates all the way to a value, where small step semantics are going to sort of evaluate along and give us intermediate A expressions until it finally gets to a value. So we're going to get to that a little bit later in the lecture. But let's look at this big step. Now remember, this arrow, this means really that this A expression, that one, paired together with the value -6 is an element of the arrow relation. Remember, arrow is a relation between two things. I mean, that's potentially confusing here because we've used arrow in the past to denote functions. It turns out that for the big step semantics for A expressions, arrow is a function because any individual syntactically correct A expression will only evaluate to one possible integer. That's because our rules are deterministic. It's more interesting to talk about deterministic rules when we are in the small step semantics, but you can sort of see it here that there's really only one rule for each operator. So that means you can only go one way for each operator. And there's only one rule for this, and there's only one rule for this. So that means our rules are going to, our evaluation is going to turn out to be deterministic. In other words, there's only one derivation tree justifying this, and you could never have a different value over here on the right than -6. So what that means, for example, is that if you take the A expression 5 plus 1 times 8 minus 9, where 5, 1, 8, and 9 are all numerals, and try to pair that with any other numeral, you will not be able to prove it using these proof rules. And that might be a good thing for you to try to do, like on your own, and see where does it fail. So now we build derivation trees by using a matching kind of algorithm. We look at the A expression here, A. So we're looking at this thing, and then we're trying to see which rules do we have that can match that on here. And since it's a binary, it's a plus. It matches to this rule when you replace this circle times thing with plus, I'm sorry, with a times. It's a times. So you replace circle times with the times. And so you look at this, you could say, okay, look, my A is of this form, where A1 is the subtree representing this linear expression, which is left paren, numeral 5 plus numeral 1, right paren. And A2 is, this one, the 8 minus 9 numeral in parentheses. So what we do is we look up and we look at the rule and we say, okay, we got a plus there. I need to show that A1 evaluates to something and A2 evaluates to something. And, because we're like gods and we can do arithmetic in our heads, we can pick out the right thing to go here. But the way that we can write an evaluator that does this, and when we don't necessarily know the answers to these. But anyway, so here's what I get when I Tim.
Quick question. So, once you evaluate the numbers, is it always coming out to something that's not a numeral? Just because they're not
Right.
underlined?
Yes, the rule for this says n evaluates to v, and v is an integer. So every time you evaluate a numeral, you get an integer. And when you get to the leaves of the tree, this derivation tree, you'll see how we end up evaluating, numeral 5 becomes 5 and numeral 1 becomes 1. But for now, we still have numerals.
Okay.
Here, everything on the left side of the arrow, these are still A expressions here. Okay? And so this is the first rule. We match A. I mean, you have to, you have to figure out what's the principle. And if we have implicit precedence rules, then we'd have to be able to figure out, like, what is the principal connective? In other words, what's the name of the operator that's at the root of the tree? And in this tree, it's perfectly clear because I've written parentheses. And I guess you could sort of always assume that all of our things are going to have be fully parenthesized to leave no ambiguity, because this is really not a linear expression like this. It's actually the tree. And we'll see in Haskell, what we mean by that. But it's actually a tree with a star at the root and a left subtree with a plus, and then a left subtree with that with a 5 numeral, and then right, and so forth. I don't know. Did I explain? Did I answer your question?
Yeah. Thank
Okay.
you.
Looking back and watching my videos, I can see that, well, last time I was a little grumpy, and that's because I had just come from a faculty meeting like 0 minutes before this. And then I also noticed that I kind of run over people. I'm telling students, please ask questions. And then I kind of have a habit of running over you and not listening to the full question. And I'm going to try and do better with that. I'm kind of anticipating your question and answering what I think your question is without necessarily listening as well as I should. So I apologize for that. So anyway, so here's the first part of a derivation, but it's not complete because we need to get down to the leaves. So you can look and you can say, okay, look at this part of the derivation. We need to complete that. So now you say, okay, A is left paren, numeral 5 plus numeral 1 right paren. And so by the paren rule, this evaluates to this can be seen to be 5 plus 1, the numeral 5 plus 1 in parentheses evaluates to 6 if the numeral 5 added to the numeral 1 evaluates to 6. And there's a little bit of a tendency to want to skip this one because you sort of think of parentheses as like not really being there, but they're there in the derivation. So so we get to here, but we still don't have something. So now we need to look at this thing and we say, okay, here's my a. Numeral 5 plus numeral 1. And rule applies. Well, it's the rule for addition. And the rule for addition says go up here for the left subtree, which is the numeral 5, and write down a branch for the right subtree, which is the numeral 1. And then it should be that whatever this evaluates to plus whatever this evaluates to is equal to that. So this is verified. And, you know, we might write lines over the tops of these because we do have a rule that says num BSS, and that's a really ugly 5, but that's a 5 goes to 5. The numeral 5 goes to 5. And if you continue in this way for the entire thing, here is the derivation that you get that justifies that this paired with this is in the relation arrow. But you've also, in this derivation, you've also shown that this numeral plus 1 in parentheses, 5 plus numeral 5 plus numeral 1 is in the relation with 6, and that this is in the relation with minus 1, and that this is in there, and so forth. So all these have been shown in this one derivation because, you know, I can take this part of the derivation, and that's a derivation that shows that the numeral 5 plus the numeral 1 is in the arrow relation with 6. So I don't know. Is there any question? This is, you know, you got to follow at each step. You look at a rule, and even when you get up here, you go like, okay, what's the rule? And I didn't have room to write down the names of the rules to the left of all these, but I should have probably, to be, you know, formally correct. This should have been, you know, the multiplication BSS rule, and this one should have been the paren BSS rule, and this is the paren BSS rule, and then this is the addition BSS rule, and going from here to here is the minus BSS rule, and justifying this is the num BSS rule, and this is the num BSS, num and num. So any questions about that?
So I have a quick question.
Mm-hmm.
So basically, what does the arrow relation do again? Does it just relate like numerals to actual integers?
No, it relates A expressions to actual integers. And it's providing
Okay.
us with the meaning of an A expression. So, you know, I don't know. I guess maybe if I, can I switch what I'm sharing? Because I could go here for a minute. I mean, one thing is that, I think I'm practicing with this Wacom pad, so it's not quite as bad. But, you know, there are a lot of, now, let me see. Okay. You know, there's a lot of different, you know, like for example, let me do one. I could say like, okay, like we know that, let's say, well, I mean, you could look at there's a lot of the point that I'm trying to make here is that, you know, there's lots of expressions that evaluate to the same value. there's lots of different A expressions that all evaluate to 6. In fact, there'd be an infinite number of them. So, the things over here on this side, these are A expressions. And then the things over here on this side are integers. I know that dark green is pretty almost like black, but okay, whatever. These over here are integers. And these over here are A expressions. And if you recall, the thing to keep remembering, and I know this is like, it's a little annoying, and they're almost like trying to break you of the habit of thinking of this like this, but, arrow is a subset of A expression. Oh, it's just AEXP, sorry. Of A expression cross int. Hey. Okay. So there's lots of A expressions. And really, the way to think about these A expressions, like I was saying before, is that you should think of something like, whatever, 6 plus 0. This really is an abstract syntax tree, an AST, that looks like this. Plus, and on the left side is, I'm sorry, see, I did it. It's very easy to forget about the parentheses. It's really a parenthesis with one subtree, and under that subtree is one that has a plus on it, and the left subtree there is the 6, and the right subtree there is a 0. So this is just, like linear syntax corresponding to the structure of the abstract syntax tree. So, you should really be thinking of, I don't know, how can I go back? Let's see, down here. Okay, go back. You should really be thinking of, so these things are all in there, but this thing here gets replaced by its actual abstract. So this should really be not an A expression, but it's an AST for A expression. And the reason for that is because abstract syntax trees, there's no ambiguity in the possible meaning of the thing. I'm not confused about, A times B plus C. Whoa, which tree is it? So, naming this thing here, this is, big step semantics. Relation. You really need to kind of like think about this thing as a relation. And what we're able to do here is, by these derivations that we're building, is we're able to show that, for example, 6 plus 0 comma 6 is in arrow. And I think he sometimes starts labeling these later by like, A expression, because he gets a bunch of different ones. So any questions? Let's see, is there a way to go back? New share. Well, you should try playing around a little bit and writing down some of these derivation trees. I don't. Maybe I have to close that. Okay. Share screen. So now he tries to, he does, it's okay. I mean, I don't know. Maybe if I'd read back from this a little bit, I would have seen something about the description of rules. But he says a derivation tree, the formal definition of a derivation tree is given as follows. That let me go down just a little bit so we can see the entire definition on one page. So if there's a finite set of rules, and he calls them R, and then we assume that a subset of R is a set of axioms, and those are rules that have no premises. There's nothing to show. Like, for example, in the example that we've been working with, the rule for numerals is an axiom. It doesn't depend in any way on recursion. And so that's what the axioms are. And the definition, a derivation tree is a finite node labeled tree whose nodes are labeled by transitions as follows. And so I'm not sure he really wants to say labeled by transitions. It's more like the nodes are labeled by I don't know if I agree with this wording here, but anyway, the leaves are labeled by axioms in A. And so if we go back up here and look at our tree, this is a leaf. So these trees are historically drawn in this way. And some people get really upset and say they're upside down. And, there will be people that will insist they want to write them going the other way with this at the top and these below and this below and so forth. I mean, it just makes it harder for the grader. And, you want to say, the people who want to do that say, well, it doesn't matter. Well, if it doesn't matter, then do it this way because this is the traditional way. But anyway, so here's a tree. The root is at the bottom and the tree is branching upwards. It's almost a more natural representation of what a tree looks like. So, but if you look at the leaves of this tree, they are all instances of rules of this num rule, which is an axiom. The num rule has no premises. You don't have to show anything in addition. You just write this down if the numeral n, when you translate it using this fancy notation, you get back a value is equal to the integer v. So the leaves of these trees all are labeled like this with axioms. And so I would claim that, the label goes on here and the label is between the nodes, but okay, whatever. And a node labeled by C, all right, well, so he's just describing the structure. So C is kind of considered the conclusion of the rule. And it has descendants labeled P1 ... Pn if there exists a transition rule of the form that looks like this. C goes to Pn1 ... through Pn. Now, in all the rules that we have, I hope that's not making you like dizzy or something, but here's our rules. We have rules that have two premises. We have three of those, one for plus, one for minus, and one for times. We have one rule that has one premise, and we have one rule that's an axiom and has no premises. So this is the description of a derivation tree. And this is how you show that following these semantics, things evaluate to the right thing. So I don't know. I mean, is it helpful if I do one more derivation tree kind of live or, during the lecture, or is this good enough?
It couldn't hurt.
Can't hurt.
Yeah, I think that would help.
Okay, let's look. Let's see. Let me see if this works. Oops, last time that worked okay. Okay, so let's go. I need a new page. And now what did I do with my Wacom pen? That's insane. Oh, here it is. Okay. All right, so did somebody want to suggest something? I mean, it should be relatively simple, but I mean, we could start with somebody suggesting, whatever, 2 times 2 plus 7. Now, one thing I should do is, I was thinking when I did those before, I should stop. I shouldn't write down the right side, because really the way this works is you look and, the principal, I wonder if I can do like, the principal connective here is plus. This is at the root of this syntax tree. So the plus rule applies. And so in that case, this thing over here is my A1, and this thing over here is my A2. And V is still a mystery to me, because I can use this tree to do the calculation as well. And so the rule says, okay, take, oh, I want it to be black. Take 2 times 2 and see what that evaluates to. That's my A1. And then over here, see what 7 evaluates to. And so now the only rule that applies, this tree has as its root a left-right paren with a multiplication under it. So maybe I should label this with the rule. This was plus BSS. And now I'm using paren BSS. So that gives me 2 times 2 arrow something. And now again, here's my A1 is just a 2, so I get a numeral 2 goes to something, and I get a numeral 2 goes to something. And then I look at the rule and it says, oh, the num rule. Okay, so this was the times BSS rule. And then this one is, okay, that's a 2. That's the num rule. And this is a real 2, an integer 2, and that's also the num rule. And then over here, this is a 7, and that's the num rule. Well, so I should start coming back down, though. This value here has to be 2 times 2, so this becomes 4. And on this rule, whatever this evaluates to the same thing. And so that's 4. And now this one here with the numeral evaluates to 7, and then 7 plus 4 is 11. So you kind of, one thing that the more static version of my notes doesn't really kind of show is that how values are coming down the tree to form the new values. Well, I mean, and 4 and 7, I kind of messed that up. To form new values. And if we look at the code for an evaluator for this thing, it's just, you know, taking that. So this comes down together with this to give you the value 11. So you can work up the tree, you know, this maybe up. I should use a different color. Let's see, you know, this goes up, and then this goes up, and then this goes up, and then this one goes up here, and this one goes up here. So information is kind of like flowing up the tree to be able to build the complete tree. And then information, once you get up here, you know, up here, now I have enough information to figure out, okay, 4 is equal to 2 plus 2. I don't know that until, you know, but you can eyeball it and write down the right derivation. I mean, the derivation tree I showed you before looked just like, you know, something like this whole tree here without all the scribbles. Questions? Okay. That's funny. When I'm sharing the whiteboard and I want to go back, it doesn't let me. Okay, so now, where's the other? Come on, little mouse. Oh, I don't know. Zoom really sometimes acts very strange. I apologize. Let's see. So we could let's look at the Haskell code. And so this is for these A expressions, but we don't, this is the evaluator for the A expressions, but we don't have variables yet. Now, this part of the code here essentially is the code to build a derivation. And probably these things should really be called R's instead of D's for derivations. And this should be like a derivation, but the A number rule is an axiom. It just has an A expression, which it has to be, I mean, to check the proof. If you want to check one of these structures, you gotta make sure that this A expression really only is something of the form num int. Otherwise, that rule does not apply. And so here's another node in the proof tree where the conclusion is this A expression goes to some int. And then for plus, we have the left the proof of the left subtree and the proof of the right subtree. So let me see. If I go down the bottom here, I think I have some kind of, okay. Here is the code to build a derivation. And so if I want to prove that there's a derivation of num10, it says, yeah, there is. Num10 evaluates to 10 by the rule a num_d. I mean, actually, why don't I just fix that now? This is maybe confusing because these labels are really the rules. This is dangerous. Global replace D with R. Well, it might work. I don't seem to have any R's. Missed one. So these are the rules. And I missed one. There it is. All right. So now we could make a nicer display for this because I could say, I could write num10 right arrow. Oh, I think I have that somewhere in here. So this is a Haskell implementation of building the actual derivation structure. So maybe if I say derivation parts. Then it says, okay, num10 evaluates to 10. But, so now I could prove the one that we just did, which was, I forgot, what was it? It was,
it was 2 times 2 plus 7.
okay. Okay, so A plus, I think it's just plus, is it plus BSS? What's this constructor? It's just plus num2, and then I think it's mult num7. And this is a representation of that tree that we wrote, where the top, the root at the root of the thing there. Now let me just look at the derivation parts of this, and maybe, I don't know, it shows all the different individual parts. Oh, did I write down the wrong thing? It was plus 2 times 2, so this should be the mult. Okay. I should switch mult and plus there. Okay, so now I get plus mult 2 num7 evaluates to 1. And I mean, we could write a little pretty printer for A expressions. num7 evaluates to 7, molt num7. Oh, but except that I didn't do it quite right because I got, this is actually parent. I don't know why he calls it what the T is doing there. Paren seems to make perfect sense to me. Whoops. Do I not have it in my constructor language? A parent. Because I need the same one for every language. He has one of these parent things. And so I need to distinguish. This is an arithmetic parent. And so where is, though, the A parent? I've got plus. It seems to be like I'm missing an A parent. Is there a bug in my code? Shouldn't there be one more? The left, this is the right num7, but this one should be, am I not displaying A parent properly? Okay, well, in any case, I gave you the code. You can play around with this. I'm just surprised I'm not seeing an A parent mult here. But maybe derivation parts is not really showing. The right thing. So now what's going on here? One thing is that I can just use instead of prove, I can use big step A prime and apply that to this, and it tells me the answer is 11. So what's going on with big step A prime? Well, this thing, each one of these looks exactly like, for the plus case, it looks exactly like our rule. It says, okay, we've got a plus A1 and A2, and those are A expressions, evaluates to V if I recursively evaluate A1 and then recursively evaluate A2 to get V2, and then add V1 plus V2 to get V. So now this looks exactly like the rule, except that this is a function. Like, what's the type of big step A prime? Whoops. It takes an A expression and returns an int. So this is evaluating it. So what's happening here is that implicit I'm like all of a sudden uncomfortable. I can't see myself. Okay. Implicit in the recursion that this big step A prime function follows is the same as the derivation tree. See, it makes a recursive call here for A1. Now, it doesn't display the tree. It doesn't build the tree. It's just the recursive. If you sort of wrote out the recursive pattern of a call to big step A prime, you would get something that looks like the pattern described in this thing that's kind of explicitly representing the derivation. So the unfolding of the recursion, this one here is, and really it's the prove function, and maybe it's something's wrong in prove. Let's see. I'm not sure why I'm not seeing that an A. There should. It seems to me like there should be two A parents in the derivation parts of this proof, because the left subtree is somehow invisible here. There are two of them. This one just doesn't have the A parent on it. I don't understand why. Well, so that's a little debugging that maybe we could do later. So I don't know. Your homework is now to basically, I've given you the B expression syntax. And your homework is to write a function like big step A prime for big step B prime. And so to write an evaluator for this thing, and then to make your own derivation type for Boolean. So you should have like a data. You're going to need to make something that looks like, data BSS B expression is equal to, and now for each of the rules in the big step semantics for BSS, you're going to have a rule for that. And you can look on the book and see what he calls the rules and name them, like B. I don't know. I think there's like an EQ. Okay, equals rule, and that has an A expression, which is better be, when you do the proof part, that better be a B equals. And now we have a bool that we're evaluating to. And if you look at the rule for equals, it's going to have, like, it's so interesting here. It's going to have two subparts for A expressions. You could look just at the syntax and tell the rule for plus has to have two recursive parts. Okay, the rule for plus has two recursive parts. The rule for mult has two recursive parts because we're defining mult. Mult is a constructor. It takes one A expression and then another A expression and returns a new A expression, which is the multiplication expression. In the proof, we're kind of making the recursion explicit. So you're going to have something like this, and then you're going to have like two BSSB expression, maybe I should say derivations. I don't know. I could probably just say well, I don't know. All right, if I want to keep it with what I gave you, it's going to be like this. And then we're going to need a rule for, what do you do? And the thing is on these big step semantics, the rules follow exactly the syntax structure. So, we don't even need to look at the rules, and we only have one. We don't even need to look at the rules for these yet. You can go here and you can say, okay, I'm going to have a BSS greater than rule. I'm going to have a BSS not rule. Now, this one's only going to have one child in the tree. So these are the children that you have in this tree structure. When I apply the plus rule to this A expression, which, in a richer version of Haskell, I could restrict this here and say, oh, this better be like an A expression. I'm sorry, a plus A1, A2, right? Because I know that has to be a plus if this rule's going to apply. But I can't really say that because I'm at the type level here. There are versions of the type system that would let me do that, but we've never, they're more complicated. This is dead simple Haskell, though, except maybe this thing is a little bit more interesting. You're building a tree to represent a derivation, whereas this one is just evaluating a expression. Are there any questions? Has anyone started trying to do this? I did put it up, didn't I? Has anyone seen
I don't see it.
Oh, you don't see it?
I don't think it's up.
Oh,
No.
okay. Hang on, let me go to Wild Web. I thought I put it up the other day. God. Oh, is it? No, we still have a few minutes. Aha, I haven't published it. I thought I did. Okay, sorry about that. All right, now, unless there's questions, let me go to the other notes that I made from today to talk about this, to go on to the small steps of semantics. So are there any questions? So the difference between the big step semantics and the small step semantics is that the big steps take, could be a huge arithmetic expression and evaluates the entire thing down to a single integer. In one step, the arrow relation takes an A expression and pairs it with an integer. And in here, for the small step semantics, you're kind of doing partial evaluation. So we don't just have before, all of our transitions were from A expressions to int, but now we can have A expression to A expression transitions. And that just means, oh, if I evaluate one part of this A expression, I get back the next thing. And we'll see when we look at the rules. So now, for convenience, he, Huddle, extended the syntax to include integers. So now I have not only numerals, but I have actual integers, but there will be no rules for just of the form v arrow v to do something directly to a single integer. Otherwise, we'd get stuck in a loop. The V's are allowing us to say, oh, this part of an expression A1 evaluates to the integer 7, and now we'll do the right part. So here's the rules. So each rule that we had before, we had one rule, and now we have 3 rules for each constructor, for each different operator that we have. And so we have one rule that says, okay, compute in the left subtree. Go over here and pick out the left subtree of the plus. And here you can, well, I don't know. Let's see. It's interesting. It's still hard to see. Oh, no, here it is. You see the difference between the plus in the syntax here and the mathematical plus. I mean, it's so hard to see what he's doing here, that these are still just syntactic symbols, and this over here is a mathematical symbol in the domain of integers. It's real addition. But anyway, one thing you could do is you can go to the left subtree and you can do a step of computation. Now, this is small steps, and he uses the big arrow. I don't, It is non-deterministic. So the other arrow, which looks more like a function, is better, but maybe the correct one to use. So you can either go in the left subtree and do some computation, or you can go in the right subtree, A2, and do some computation. And so like if you decided to choose this rule, you go and you do some computation in the left subtree, and you get back an A1 prime, and then you replace that for A1 in the new expression, and now you've gone to this. And so you have the same thing for times, and you have the same thing for minus. And now we have, except that the final case in all of these is, once I have something that's of the form of value plus a value, only reduce plus, the actual plus, when A1 and A2 are actual values. And then down here, you've got 2 rules now for parentheses. And this one, it says, okay, go and do some computation in the thing under parentheses. That gives you A1 prime. Put that there. The only eliminate the parentheses when you have an actual integer in the expression there. So let's see. All right, let's look at some of the derivations that you could do. You could say like, this A expression evaluates to this A expression. And what I've done is I've gone in the left subtree argument and I get back 5, and then I replace the 5 coming down, and so I go to here. So this derivation here justifies that this is in the small step semantics relation to that